I've been working with different sorts of environmental sensors for quite a number of years and have used oxygen sensors, including the newer optical ones, for quite a while too. But I've spent the last 6 months working intensely on a range of different oxygen sensors while on sabbatical with a group at Lake Tahoe, and so I'm going to be talking somewhat about that today, and trying to give people advice on how to get the best data out of oxygen sensors. I think that we have a choice of very high quality products. There are pros and cons to virtually every one out there. There's not a simple good answer, but I think it helps to learn how to use them better and how to choose them better. And so I have a little bit of orientation on what people might do with oxygen sensors and what some of the issues are before talking about calibration and then some measurement strategies. And at the end, I'll just briefly show the range of sensors that I've worked with, talk a little bit about their properties before we go into the demo. We'll have, let's see, 4 or 5 different types that we conceivably could compare today, but probably we'll just compare 3. The field comparison may end up being some data we collect after the talk that I show you tomorrow, so we can fit it in with the weather. Some acknowledgments. First, I've been working with Jeff Schlotto at the University of California, Davis, who heads the Tahoe Environmental Research Center. Lacawac Sanctuary and Leslie Knoll have helped a lot with the data collection here and access here at my own university at Lehigh. Has been very supportive. And Michael Head's been great too. He has volunteered to donate a mini-dot data logger to Lacawac, and this would be a good chance for you to do that, Michael, if you want to come up and give that to Leslie. In spite of the importance of oxygen, we have not had a monitoring oxygen sensor in the lake. So thank you very much. We will use it in good health. And you'll see that it has some really outstanding properties too. So we're not getting an oxygen sensor that we'll regret, I'm sure. So we've heard about the objectives that I'm describing here in different talks today. One of them is that people often use them to characterize a lake habitat. And I will make the point here that if you calibrate them carefully and you take care to achieve stability during the calibration, it will help you when you're comparing dates and sites, because it doesn't really make much sense to have a sort of a half-baked calibration and then try and draw some inference about changes. Temperature sensors now are readily available with far better than 1/10 of a degree Celsius accuracy, and we expect that. Most oxygen sensors have a nominal specification of about 5% accuracy, and it's much worse than that if you're not careful. So what I'm trying to do is bring the quality of our data from oxygen sensors closer to what we can expect from temperature, and so some tips. We can look at the effect of oxygen in the environment as being suitable for animals as one of the habitat questions. Hypoxic and anoxic zones are very important for animals. Some need it, some can't live in it, and so we need to be able to characterize those properly. Lake metabolism has been discussed extensively and can be estimated even by a single oxygen sensor in a lake, although more sensors is better, or a profiling sensor. And taking into account the gas exchange at the surface allows you to make these estimates, and with them you can determine phytoplankton gross and net productivity if you have a time series. Community respiration, ecosystem metabolism if you make more assumptions about who's doing the respiring. Even something like photobleaching, dissolved organic matter, is a highly oxygen-consuming process, and it's rarely taken into account in metabolism studies, but can be important in high DOC lakes exposed to high sunlight. And even more, reactive molecules can be produced by the sunlight that consume oxygen or react with other molecules later. So there's a whole suite of things that you might characterize under metabolism, and good, sorry about that, good data, good calibration and understanding of your sensor will help you get better data of this sort. So I'm going to start talking about some Lake Tahoe data. And can you see around me that way? Okay. And we're here in northeastern Pennsylvania. I'll talk about Lacawac examples at the end. And Lake Tahoe is here on the border between California and Nevada. And it's a lake well known for its clarity and early efforts in the 60s to mitigate eutrophication by exporting wastewater from the basin. It now reaches peak human populations within the basin of 300,000. So it's a pretty good sized city, and yet it's a high elevation lake, very deep, and still oligotrophic, although with issues they're trying to address both in nutrients entering the lake in spite of the redirection of the wastewater, and small particles, fine mineral sediment particles entering the lake from stream runoff that's been modified over the years by human impacts. So I'm going to give you a couple of different examples here of showing the kind of oxygen data that would be intriguing to look at habitat as well as metabolism and characterize the lake at different scales. So here, the first one is in Emerald Bay in this area in the southwest corner of the lake. And in the mouth of the bay, there is a shallow area that's being tested for a technique to rid the bay and the lake of some invasive clams. The clams come in on hitchhiking on boats, and they're known to be in a few areas around the lake. And one strategy that was developed and is now being tested is to put rubber mats on the bottom. Roll out large rubber mats, try and smother them. You know, bivalves in general do pretty well keeping their shells shut for a long time and can tolerate anoxia, but if you smother them long enough, they will die. And so how well is it working? Well, for 6 months now, the water has been tested with oxygen data loggers, including mini dots, the kind that Michael just gave to Leslie, placed under the mat and above the mat in different positions around Emerald Bay to see how effective the mat is. And the goal is to see if there are periods of time when the oxygen gets low enough for a long enough duration to kill the clams. And here is data logged at 10-minute intervals, both concentration in milligrams per liter, and in blue I think is percent saturation, and then black is water temperature. And these are just 3 different models. This one was deployed either later or we don't have the earlier data set. And you can see that there are periods, especially later in the spring. The dates here go from February to the beginning of June, February to the end of May, and this is March through the end of May. They're more or less lined up. And you can see periods when the oxygen gets low, and especially later in the spring, it gets down to pretty essentially zero, sometimes for a prolonged period here, and not quite to zero there. So one point I'll make is that if you want to try and interpret this data, you need to know how close to zero is zero. You need to calibrate these at zero oxygen so you know if that's really zero or just low. And you want to make sure that they're all performing well and are giving you good data, that clocks are synchronized and so on. They're comparing these with another brand of data logger. They have a couple of ZebraTech Diopto loggers in the system too. And one of the issues you run into when you're comparing sensors and different people are involved in deploying them is the time base. And that's partly why I raised the question with Luke earlier about specifying the time base. It wouldn't make sense if some of the loggers were on one time base and some on the other and you didn't know that. So Michael's product very cleverly keeps track of UTC internally and then generates your local time as you wish when you spit out the data in a text format. For which I applaud him. I don't know of any other data logger that actually makes an explicit effort to keep track of time reference. Usually you get a data set that says time. That's it. And what time? Who knows? Just depends. So let's see what's going on here. There. Okay, so a second example of oxygen in Lake Tahoe is a sensor that was put down in the winter in one of the deeper parts of the lake. The lake is over 500 meters deep. At this point that you see is 465 meters deep on the just off the eastern shore. And in this case, the sensor is a Rinco fast oxygen sensor. It's got a specially designed membrane that responds in a second or better to changes. So it's actually one of the best ones suited for profiling, where you're raising and lowering the instrument. But in this case, it's used also because it's stable and it's sitting at the bottom. And here's the record. The concentration in micromolar oxygen is shown over here, which is about 30 times milligrams per liter. And this is recording, I think, at hourly intervals, so the data are less frequent. But you see that even at the bottom of a lake where you might expect not much to happen, there's a lot of fluctuations in the oxygen. The black line is temperature, and you can see they're pretty highly correlated. Up here you see a plot of oxygen versus temperature. Temperature here, the range of temperature was an amazing 5.03 to 5.06. These are very sensitive to small changes in temperature and very precise, sort of oceanographic scale sensitivity. And most of the data falls along this curve, which is actually the opposite of temperature solubility. At the higher temperatures, you have more oxygen in the water. Colder temperatures, less oxygen. We all know from our study, the basic studies in limnology, that oxygen solubility goes the other way. So and since we've just gotten this data, we don't know why, but we suspect that this reflects movements of water masses where the lower temperature may reflect a longer residence time in the bottom of the lake and maybe more time for the benthos or sediment, active sediment microbes to consume oxygen. Time will tell. We don't have any other corollary data with it except specific conductance, which was also recorded. And that shows that two of these fallouts were, which you see plotted here in brown and green, were sort of anomalies of specific conductance. What does it mean? Well, basically different water mass may be a different source. So it's really going to be interesting to tease what's happening here. And what I would like to do is combine this sensor with a fluorometer that can detect CDOM and algae and turbidity to go along with this basic data. So a third example in Lake Tahoe is one that was recently installed at the end of May over here on the western shore and closer to shore. And in this case, it's an Andera optode, a fourth brand that I'll have mentioned. And it's not as fast responding as the Rinco, but pretty fast, about 7-second response time. Used very widely oceanographically, very stable. It's attached, like the Rinco was, to an RBR global data logger, and this one was at 108 meters in the water, about a meter off the bottom. And we're collecting data here at 30-second intervals for everything. Normally, power is a limiting factor, but we have a cable to shore that's providing power and delivering data by telemetry, and it's 525-meter long cable. And again, we see rapid scale fluctuations sampled at 30-second interval. You see about the same pattern if you sample at 1 or 2 minutes or maybe 5, but if you sample less often than 5 minutes, you start losing some of the interesting details here. What it means? Probably the same kind of thing that we saw with the Rinco, different water masses. If we look at a correlation between oxygen and temperature, it's the same qualitative scale. Higher temperatures, higher oxygen, lower temperatures, lower oxygen. So the same thing's happening here in the shallow bottom area as the deeper area, but we don't really fully understand. We don't really know what it's doing. Here is a vertical profile of oxygen at the end of, at the middle of June, and you can see a peak in the area of peak productivity, about 50 meters depth. The depth scale, unfortunately, is cut off there, but this, the peak is around 50 or 60 meters, where you tend to see the peak in the chlorophyll biomass, and the productivity is a little shallower than that. So we're getting high-frequency data. Here's a temperature versus depth profile show from the end of May to the middle of June. The lake became stratified somewhat with warming and had a few reversals. So conclusion here is basically the lake is very dynamic, partly because of mats put down at the bottom on purpose, but partly because of processes that we still don't understand, probably related to mixing. And they have implications that are quite important. A recent model predicted that Lake Tahoe might become anoxic in 50 years because of climate warming. It's hard to believe. I'm frankly truly skeptical, but it's based on some sediment oxygen consumption data in the laboratory from Lake Tahoe. We already have data from the Rinco sensor showing that following stratification in May, the bottom sediment consumption might be around a third of what was estimated in the lab. So that already can go into the model, but we're hoping that once the lake becomes more stratified, we'll get an even better estimate of that consumption factor. All right, so what I'm going to talk about, now that I've set a little bit of a context for the kinds of questions one can address with oxygen sensors used in different ways, is some of the issues, some of the problems or difficulties in making measurements. And one of them I alluded to earlier is just getting a good calibration. And it's often a challenge to create a standard condition for a user in the laboratory in order to put your instrument into it and see what it reads. Probably the gold standard is an oxygen-air mixture, either a gas mixer with pure gases or commercial mixes that you perfuse into an air chamber, and you can see the response. Most people don't have access to that kind of tool. The most widely used, say with YSI oxygen probes, is you put the chamber, you put the sensor into a humid chamber, so it's got air in it and water vapor, and you let it stabilize at a constant temperature, and you can calculate the equilibrium value because the air partial pressure is the same as in the water. And the only problem is it's hard to get the temperature to be totally stable unless you control it well. And if the temperature drifts, or if the membrane and the electronics controlling the temperature versus the oxygen detection get out of phase at all, you have an error. Another way is to put it in water and bubble air into the water until the air bubbled into the water reaches equilibrium with the solubility. Not always easy to achieve if you don't wait long enough, or if you have something, microorganisms consuming oxygen in the water, or if the temperature changes because the solubility changes with temperature. So there's calibration issues. And finally, in all these oxygen sensors, they have a signal at zero oxygen that's not zero, and you need to account for that for accurate readings, especially if you're doing something like the Emerald Bay example where you want to calculate how close to zero you get. So I'll talk about examples of that in a few minutes. There is the issue of spatial versus temporal variability. We often end up deploying one or a few fixed depth sensors in a lake because that's what we can afford, but then we don't know about what's happening elsewhere. And you often have to make a tough decision. What's the right depth? Lakes change seasonally, and so an even better response, if you can, is have a profiling buoy that measures oxygen, have it go up and down. But then when you put one of these optical oxygen sensors onto it, it may respond too slowly to keep up with the rate of movement. And you have to worry about whether when you go from a high oxygen at the surface to low oxygen deeper down in lakes like Lacawac, have you waited long enough to reach a true equilibrium? The slow response is also not always well characterized by manufacturers, and it changes with temperature. So I'll talk actually about a strategy for coping with that later. And if you have separate temperature and oxygen sensors, they can respond at different rates, and that's almost always the case. Even with the fast responding Rinco, the temperature sensor might not track the oxygen change if you're trying to profile with it, so you have to take care with that. In anoxic conditions, the old-fashioned Clark electrode, which is still very effective in many cases and responds quite quickly, the one with the membrane and the fluid you put under it, and you hold it with your thumb and pull the membrane over and put the O-ring on. Well, those can be inactivated by hydrogen sulfide, and so the optical probes give a big advantage over that because of their stability. And so I'm not going to talk about those today. Yes. I'm sorry. Yes. Arthur, come on in. Come and say hi. You heard about Arthur Watrous when Leslie introduced this session today, the founder of Lacawac Sanctuary, and we'll wait for a moment while he comes on in.
So Arthur donated all this land and created Lacawac Sanctuary.
So this is Arthur Watrous. You saw him in a picture a while ago when Leslie did the introduction. And he is the one, he and his mother basically are the ones that are responsible for Lacawac being a 501c3 independent nonprofit with a mission of preservation, education, and research. It was his vision back in the 60s, and his land, his buildings, and it's his donation that has made this all possible. So I want you to help me welcome Arthur.
Keep coming.
I'm talking about measuring oxygen, Arthur. Measuring oxygen in lakes, the oxygen we breathe. So you can read up there, see? Okay. And one issue is when you put out sensors for a long period of time, biofouling is inevitable, and some lakes are more productive than others, and it may only take a week to have problems. If something grows on the sensitive surface of your oxygen electrode, it may consume or produce oxygen and give you an artifact. So I have some ideas about how to detect that. I don't have any unique insight into how to prevent it. Some people put a copper foil around the sensor or a mesh over it, and it works. Some of those methods work in some settings and not in others. But I have some ideas about how to detect it. And I think everyone should try and detect biofouling in their sensors to know if it's a factor or not. I'm going to skip pretty quickly over calibrating sensors to show you some examples, but the basic issue is you can put the sensor into bubbled water or into humid air, and in each case you've got to wait until you get a steady signal, and ideally keep the temperature constant. It's something that benefits from a laboratory setting, although I do have some strategies for doing it on a boat. When you're calibrating these, you need a barometer signal, and because the pressure of oxygen is called the partial pressure. It's a fraction of the total atmospheric pressure, and the sensor actually detects that oxygen pressure. So if you calibrate a sensor at sea level and then you take it up to the elevation of 6,200 feet where Lake Tahoe is, you're going to get a reading that's about 60% of the sea level reading just because of that. I prefer a continuous recording of barometric pressure because then you can have a continuous recording from your electrode while it's in the calibration chamber and you can correct for it, but a single handheld barometer might do. But what you must avoid is barometers from a weather station that are corrected to sea level, because that's the standard for weather, to correct the barometer to sea level. You don't want that. You want the real pressure at the point where you're making your measurement. And I'm going to skip over the advice. We can talk about this in the demo afterwards, where I will show you how we're going to do some calibrations. But I will say that for testing the biofilm effects on a sensor, the simple approach is bring your sensor back from the field where it's been deployed, put it uncleaned into a calibration chamber, whichever one you prefer, but it's worked best in water. Measure its response for a while under standard conditions, then clean it and measure it again. And if the signal goes up a little bit or down a little bit, then obviously cleaning had an effect. If it's a very small effect, you can pretty well assume that biofilm effects are minimal. The very best way is to put it in a small volume of water with no mixing and repeat that test, uncleaned and cleaned. And you may be able, if the temperature is right, to actually recreate the magnitude of the effect in the lake before you retrieved it and then correct for it that way. I can talk more about that later. Zero calibration is another issue I alluded to earlier. And several manufacturers, including Mike in their manual, from PME, suggest putting some sodium sulfite chemical into a bucket of water, a certain proportion. Chemical absorbs oxygen. You put your probes in the bucket and cover the surface so that no more oxygen is diffusing in. And he suggests a plastic film. I would just add that bubble wrap would be much better because it won't sink. I actually have some plastic floating beads that are even better because they don't need holes cut in them, and you can just throw them on top and they cover the surface. And then if you want to know the effect of temperature on your 0 point, you can put this bucket in a cold room and let it gradually cool off. Or you can start it with an ice water mix and let it gradually warm up. And you'll get a nice curve that you can use to field correct your data, which will of course be recorded at a range of temperatures. I've come across a novel solution that I was skeptical of at first, but I've tested it now and I really like it. Most of us who have worked with sodium sulfite would prefer not to use it if we don't have to. It's a little bit of an irritant. It will cause irritation to your eyes or your lungs or your skin, and it can create a little bit of hydrogen sulfide gas as it degenerates. Baker's yeast. Buy it at the supermarket, dry active in a little foil packet. Works great. add some sugar into warm water, the oxygen goes to 0 in a couple of minutes. And then put it in your cold room. And as long as you cover it, the yeast will be inhibited by cold temperatures, but if they do their job in the warm solution first and then you cover it, it will stay anoxic as you see the temperature effects. And then you can just wash it down the sink and not worry about any contamination. You don't want to do that, however, before you do 100% saturated. You don't want to get the yeast into your water that you want to be 100% saturated. You want that to be clean. So this is best to do last if you want to check the performance. Here's a picture of the sodium sulfite solution on the left and the dry active yeast and sugar on the right. So I've seen one manufacturer that recommends this solution. I haven't seen it widely used, but I think it has a lot of potential. Here's a couple of examples of calibrations in the lab. I'll go quickly through this. Basically, put the sensor, in this case the Rinco, in a temperature bath. Here's temperature. And it takes this long for the bubbled water to reach equilibrium because the bubbler wasn't going before I put it in there. It will respond to the actual concentration right away. The difference between this curve and this curve is this is barometer corrected and this is just ambient pressure.
What's the temp horizontal scale?
I can't see that there, but that's basically 2 days. So it was easier just to leave it for a day or two and let it run because this took about, I think I started the bath, the bubbler, right at the beginning here, and that was the problem. So it takes about a day, actually. Big bath, small bubbler, 2 bubblers. I would actually prefer that we're now changing this to use a small container bubbled in a larger bath. The outer bath controls the temperature of the inner bath, but you don't bubble all that water. It's quicker. But whatever method you use, you need to wait till it's stable and not just say it should be 30 minutes, because I think it should. Look at the results. Here we put it into a bucket of sodium sulfite, and the temperature was at room temperature. Sodium sulfite had been mixed up at room temperature, and here's the temperature gradually going down as we put it into a cold room, and here's the response. The 0 oxygen, this is a percent of saturation here, and I'm not quite sure why this is. That's temperature. Here's the oxygen over here. The oxygen signal is slightly negative, about minus 1.5%, about minus 1% at warmer temperatures. And when you plot this curve versus temperature, we get offset versus temperature. This is very useful if you're working at low oxygen, because now you can say, I know what my temperature was. I can subtract this amount from the recorded signal and get a much more accurate signal at low oxygen. This will also have a slight effect on your high oxygen signals too, because this number is a percent out of saturation with the Rinco. So very simple. You put it in a bucket, cover it, let it cool off, record the data. It's just logging. In this case, it's logging more frequently, I think, at maybe 1 minute intervals compared to the field rate of 1 hour intervals. Mini dots, the ones that Mike just showed us here, were under the mats in Emerald Bay for several months, 3 or 4 months. And here, this is corrected for barometric pressure. It reads 100% in bubbled water, not being cleaned. I turned off the bubbler just to see what would happen. And there must have been a little bit of respiration going on in the water in my water bath. It went down a little bit. When I turned the bubbler back on, it went up to here. Actually, right here, I cleaned them. I took the electrode out, cleaned the surface off as recommended, put it back in, and this was without the bubbler, and then back up here with the bubbler on. So it may be the difference between this downslope and this horizontal slope is the effect of the biofilm, but it's a very small percentage. It's a fraction of 1%. So it showed us in this case that we didn't have to worry about biofouling during that deployment. Here's another sensor that started out reading 93%. And Mike has a parameter that he records in the data set that checks the internal status of the electrode, and I haven't looked to see if that indicates there was a problem with it or what it could be, but most of them were closer to 100%. This one was lower, and since we didn't test it before it went out, we don't know if it's caused by the deployment or it just started out that way. So it's not a quality control hit on Mike's effort. Everybody should check your sensors before they go out just to see how they're doing. Here again, put them in sodium sulfite, let the temperature change, and the 2 different sensors give a small change, but the same slope, negative. So a different response than the Rinko. And it's basically because the electronics are what are dictating this. And electronics are different. So it's easy to determine what the numbers are. In this case, I'm missing this middle ground because I started these at 10 degrees and went colder, and then did part of the warm temperature later instead of starting at room temperature. But it's an easy test to get the whole temperature range if you plan ahead. Tetra Tech, I did a couple of these diopto sensors, and they both came out very close to 100%, and small sample. The zero offset looked a little bit more like the Rinko, pretty flat here and then up a little bit at higher temperatures. This was flat here, but then lower at higher temperatures. So there may be an individual variation among the electronics, so it's good to test each one. And I don't know yet whether, once you characterize this, it's always going to be the same or whether it's going to change. So the best thing is to keep testing it each time. Here's a test I did with the Andera optode electrode. I don't have one here to show you. It's attached to our instrument in Lake Tahoe, but it has a sensitive membrane here and a temperature sensor right here. It's about this big. And I wanted to do a temperature calibration for saturated water. I wasn't able to do that with the other sensors, but here's an example of how you can calibrate it with relatively simple lab apparatus. I had a water bath. I could set different temperatures. And I started out with warm water that was bubbled, and I kept the temperature at 30 degrees until the oxygen leveled off. And here's the corrected, pressure-corrected oxygen level at 30 degrees, these yellow points. And then I lowered it by 5 degrees. The oxygen dropped because of the drop in temperature, and then oxygen started being added back in by the bubblers to reach the new equilibrium, so it came back up again. Once it reached that, I lowered the temperature. So these are successive equilibrium points. These are the artifacts. If you don't wait long enough, you get the wrong answer. If I take the high points here where it reached equilibrium, I get this curve, and I've just fit a polynomial equation to it. So I could use this to correct the optode for any temperature that I measure in the field at 100% saturation. I can make this match. And if I take the zero correction that I also did with it in sodium sulfite or yeast, I can make it even more accurate. I don't know why this was reading 89 to 91%. They claim 5% accuracy. And I think it just means it's good to check. Yes, sorry.
What's the time frame on that return when you chill it? How long does that take?
It takes about 45 minutes for the bath to change temperatures. And then it takes another 45 minutes or an hour. And this was in this 3.5 liter bucket with a couple of aquarium bubblers in there. So, you know, it's on the order of, it took all day to do this test, and I would have rather done it longer.
On the order of an hour. So if you if you set up a bubble water bath, you should probably wait an hour before thinking that it's become more.
Yeah, and then look at it and look at the data.
Yeah, okay.
Yeah. And you can make it faster if you make the containers smaller relative to the number of bubblers. And you can make the temperature change faster if you use a smaller bath. So everything can be optimized. But the point is, you need to create steady conditions. And it would be even faster if you did it in humid air. But I didn't have a good system for controlling the temperature of everything in humid air. It's easy to get gradients in air. Water just makes everything be the same temperature if it's mixed. So I prefer this, but you have to wait. In the zero oxygen, these are the plastic floating bubbles, and I just mentioned that because everyone can use bubble wrap, but then you have to, if your sensors are mini dots, you just put them underneath. If you have a sensor attached to a cable, you got to cut holes around it. But we have these, so we use them. Bubble wrap is universally available. And my colleague Jeff Schlato had used these to control evaporation in a bath for calibrating thermistors, and I just adapted them because they also block diffusion of oxygen. Here's a Rinko sensor. I've now shown you a picture of the Andera optode and the Rinko sensor, and you've seen a mini dot. I have a diopto and some YSI sensors and a Eureka oxygen sensor over here that we can show during the demo. So this is where we're deploying it to 465 meters in Lake Tahoe. It's a big thing there. The sensor membrane is on the face, and in the case of RBR Global, they don't use the temperature sensor that's built in here to report temperature. They have a fast responding probe over here. But the internal compensation that's used to generate percent saturation in the Rinko uses its own temperature. So there's a possible question if you're using it for profiling that they get out of sync. So we're going to have these other samples to show you, and I'm going to close by talking about measurement strategies and then summarize. What I mean by measuring strategies is how you try and collect data. And I think the important thing is if your water is changing, you can adjust the sampling accordingly. If you know it's changing with depth, if you know it's changing with time. But if you don't sample enough depths or enough times or short enough times, you may not know that it's changing. So we were intrigued to find that when we sampled at 30-second intervals, just because we wanted the high-frequency temperature data, we found high-frequency changes in oxygen. And that's a warning that if you don't sample it, you don't know what you're missing. I still don't know what the high-frequency data means. We often see the high-frequency variation in chlorophyll fluorescence, and we assume that we just need to filter that out. But it may be a reflection of the same thing, that small water masses have a different history, and in the case of oxygen, I think that those are real numbers. They do correlate well with temperature, and that's part of the clue that tells us. Maybe that would even work with some of that high-frequency chlorophyll fluorescence data too. Time lags in sensors, I have a strategy for dealing with that. When we have to put a slow sensor on a profiling buoy, like Jenny's buoy is going to use currently a YSI 6600 series optical probe, which they call ROX. The new version is going to use an EXO sensor that's supposed to be faster, but they're still slow compared to the Rinco. How can you deal with that? This is a case which I call blind profiling, and I'm going to show you some Lacawac data now. Blind profiling means you're putting down a sensor, but you don't know the data coming back instantaneously. You may be lowered in a rope, and you download the data later, or in the case of a profiling buoy, ours is made more portable and more economical by having a dumb wire that lowers it, and it reports the data when it comes up, not while it's underwater, to the surface unit and then transmitted to shore. So a couple strategies. Here's some Lacawac data from last fall, and here we have the temperature in the water column, warmer and then colder down here. Here we have specific inductance rising near the bottom, and here we have oxygen. This is percent saturation of a YSI 6600. Actually, this is a Eureka probe, similar to the YSI 6600. And that's just a down profile. It looks nice. We're all done. Go home. Well, I always like to collect data on the uphaul, too. And we got this data. The temperature is also a little different. You know from looking at these kind of data, if you've collected these, that temperature lags a little bit. Our typical lake thermistors are a little slower than the oceanographic style that respond in 1/10 of a second. And they're also sturdier and cheaper. This also might be a slight difference in the water mass, a little internal wave phenomenon. But this is a lag in the sensor right here. So what do? If you collect a symmetrical down and up profile at the same rate of raising and lowering, you can just average them. And you can bin them together to get this curve. And that's our best estimate in this case of the true data. But most of us don't have the luxury of collecting down and up data, especially the automated buoys. You have to collect a lot of data to do this and be very patient, and you have to keep it going at the same rate. And so I have another strategy. Here's some hypothetical data collected over on a time series now for oxygen in green, temperature in brown, and depth in blue to show that it's gradually lower, deeper and deeper, and the oxygen goes up and then down in Lake Lacawac. And in this case, the time spent at each depth was a fixed period of time, and it wasn't long enough to reach an equilibrium for the sensor. And so my strategy for solving this problem, which might be applicable to Jenny's buoy in Lake Lacawac, is to do a little exponential regression of the oxygen at each time when it hasn't equilibrated yet, and from this time series, and then extrapolate to a later time when the shape of the curve suggests it's leveling off. So yes, it's an extrapolation, which is always a little risky, but it saves you getting bad data when you only have, say, a few points that you can collect. If you collect 3 or 4 points at each depth, you can probably do this. Here's the data without any correction, and you can see multiple points at each of these depths where the change was very rapid. And you could average those, but the average is not really going to be the right number. Here, is plotted again, the data using extrapolated equilibrium from these curves to give a better point. The point is it would be even better to use a fast oxygen sensor, but if you don't have one, and most of the oxygen sensors that we use are too slow to do this very well, it's extremely valuable to collect more than one point. And it applies equally well to pH data, any other sensor that responds slowly, even oxygen. So this is the response that we might have done without bad weather. I want to summarize by saying that the scientific uses of oxygen sensors will benefit from having some improved deployment strategies. Thinking about blind profiling and collecting multiple samples per depth would be one of those examples. And high-frequency sampling, something less than 5 minutes, turned out to be very valuable in Lake Tahoe. So I'm not suggesting any particular time, but think about choosing shorter times until you know the dynamics of your system, and then you can back off and use slower times as needed. Better calibration is needed by users. I think many people may just not calibrate their instruments for lack of time or not know how to do it well, but you do need a good quality barometer signal to do it well. You should do an equilibrium and zero offset value. Yeast is a convenient way to get the zero offset now instead of using sodium sulfite. And you have to think about whether you want to do it in air or water because there are trade-offs to both. Mike has pointed out that there's non-linearities in the response of these and different aging processes too, and he has developed an interesting report on how these sensors age. The good news is they're quite stable, and it's possible to detect and perhaps correct for some of the aging. But this will at least get you to two ends of the curve, which is better than none. The biofilm effect, if you leave things out for a long period of time, it's really much better to know and quantify the effect than to futilely try and prevent it, because it's really hard to keep those bacteria from growing, or algae if you're in the surface layer. And you really do need this sort of calibration if you're trying to compare 2 different times and multiple sensors, multiple sites, because otherwise differences are going to look real when they may simply be calibration errors. So I think that's it. As I said before, we're going to have a demo after this for anyone that's interested. If not, or if you do want to see the demo, it'll take us a few minutes to set up. You might want to look outside and look at the sky and get a raincoat or an umbrella to beat the storm. Thank you very much.